So, if you had to explain your Nobel-winning discovery to someone with no background in science, what is the most important thing you would want them to understand?
In fact, often you'll see people write that as the physics of microscopic quantities. But what our experiment did is showed that quantum mechanics is much more general than that, and that you could describe macroscopic quantities with quantum mechanics too, provided, of course, you set up the experiment right and do everything. And in particular, we show that in an electrical circuit, in this case, it's a superconducting circuit, where you have billions and billions of electrons having current flowing through a wire, and you have voltage across the system. The current and voltages have to be described by quantum mechanics in order to understand how it works. And a very simple way to say it is, you know, you have current in a wire, the current can flow in one direction and the other direction at the same time, in kind of the way that you describe a quantum mechanics. So it's nice you can write down the equations of what a classical response of the circuit is, and then you just go through the machinery of quantum mechanics to quantize it, which, you know, you learned in your undergraduate course, and then you can predict exactly how that system is going to behave.
Yeah, that's really great, really impressive. Yeah, it's mind-blowing that you reached that. And yeah, really.
Yeah, and it means, you know, that we build quantum systems not just with the periodic table, but we have a bigger set of components like inductors and capacitors and Josephson junctions. People have done these with solid objects, small solid objects. So yeah, we have a bigger playground to observe quantum mechanical behavior, and there have been many physicists working on that in the last 40 years to build out that knowledge.
Okay, well, to connect this with the next question, I think it is of course, for you, in your interpretation, what is the biggest popular misconception about your work that you would like to correct? What is maybe a myth or something you don't like about people are saying about your work or your Nobel winning discovery?
Oh, that's a good question. I haven't thought of that because I think that, you know, people have accepted it. And I'm going to say, I think the reason it's been so accepted is it's been 40 years. So you took the basic idea 40 years ago, and then, you know, many people have built upon that idea in many different ways. And because of that, I mean, it's just an accepted phenomenon right now that you can do that. And especially when people are thinking about building a quantum computer, building a quantum computer out of electrical circuits is such a powerful idea because we already have powerful electronic computers right now. And the fact that people have done complex experiments and all the physics works and you can understand that is, you know, a strong indication that this basic idea is correct. So maybe it's, you know, after 40 years, maybe there's, but maybe it's just like so commonplace, at least in physics minds, that it's not controversial or not even special anymore. But so I'm very pleased that the Nobel Prize Committee kind of looked back and saw that as a big moment for us. I would say the most satisfying part of doing this is actually the fact that there are few thousand physicists right now who are being employed by companies, big companies, are getting paid really well, okay, to study, you know, quantum physics and to build this technology. So they have really good paid jobs and really diving into all the details of that. And, you know, I'm glad, you know, there's all these interesting jobs that people, it's really different because nowadays, you know, you still have academia, there's other jobs, but you can also join a quantum computing startup or a quantum computing for a large company like Google or IBM. And, you know, I think that's great that people coming out, you know, college have this range of choices now, which didn't exist back then. Who would have thought that doing ultra low temperature physics would be this practical?
Well, the next question is specifically for non-specialists about your work in Sycamore. Actually, what did you demonstrate in 2019 and what did it not?
Sure. This experiment was really a culmination of, decades of research in order to understand how qubits work, how to make them better, how to put together all the elements of that, which many, many people contributed to. And it was a real team effort to figure out, the design, the fabrication, the electronics, how to do the dilution refrigerator. And, that's what was really exciting for me. But the basic idea of the experiment was to run a certain algorithm, mathematical algorithm. You're basically making random numbers, but they aren't completely random. Some of them are slightly more probability than the other. And to sample those random numbers that you make, and then you can check the statistics of those random numbers by running a full quantum simulation on a computer, okay? And it turns out that the check of whether this experiment is working right is actually quite computationally complex and requires, if you make a 53 qubits or now a few more qubits, is quite complex and hard and, takes a lot of effort. So, we built an algorithm where it was to check it required, either a supercomputer or in the end couldn't be checked at all. Now, and this kind of illustrates, for one, it illustrates the power of a quantum computer, that you can do something that classical algorithm would be very difficult. But what was lost, I almost every talk I discuss this, but no one ever talks about this. It's an experiment that checks whether your quantum computer is working properly. Because it turns out that all quantum computers have some errors in it. And what's really interesting, although the quantum computing part is very complex, the errors are kind of high school statistics, okay? Very, very simple probability theory. And, we showed that that's a really good approximation to how the errors in the quantum computer works. And that's very important because if you want to make a more useful quantum computer, you really depend on understanding the error mechanism properly. So for me, it was a very fundamental experiment to, check that it was really true. And also, if you think about the computation space, which is 2 to the 53, states that you're computing in parallel, that's 10 to the 16. So this is a macroscopic kind of size of computation that you're doing with this, which kind of is reminiscent of my thesis experiment. So I like to kind of repeating that, but in a much more sophisticated way, right?
Also, you proved that a single superconducting circuit could have like a macroscopic atom.
I would say what was interesting, and this was kind of like the 85, is this was a falsifiable experiment. We said, okay, you run this algorithm, it should work, but there is a chance it wouldn't work, okay? And you have to do the experiment and do it very carefully. And when you can do a dramatically falsifiable experiment, that's really what science is about, is you have theories. In the end, what you can do is falsify them. And it wasn't falsified, and it made sense. So that's what I liked about it as a pure science experiment.
We want to know about you also. And can you take us back to the very beginning of this, perhaps long before the Nobel? What was the specific question, paradox, or discrepancy that you just couldn't get off of your head?
In graduate school, the question, and it's actually the first sentence of our paper, is do macroscopic variables obey quantum mechanics? Which really goes to the heart of this. And this was actually interesting because the idea had been around for a while and Leggett talked about it. There were some initial experiments, but they weren't really conclusive. But we thought it was such an interesting, it's very concise, clear question. And we really liked the clarity and the fundamental nature of that question. And we thought very hard about, how exactly to phrase that first sentence in our paper. And that was really fun, kind of crafting the paper around that. And just answering that question as well as we could, to do all the check experiments, explain what the physics was, and just solve a fundamental question.
So when you are there, was there a specific moment during your research when you were convinced it was at the end, or you were ready to give up?
Yeah. So the experiment actually went pretty smoothly in the sense of the experiments, but that's because we took a very careful approach from the very beginning. And the first thing I remember talking to my advisor, John Clark, about it, my advisor, is talking about this and, okay, that's great, we can do the experiment, but what or something new we're going to do? What are we going to add to what people had done before? Now, it turns out there was a lot to add to, but we didn't know at the time. But what we decided very early on was to try to measure all the parameters so that we can compare the theory, to the experiment and really know what's going on. And this led very quickly to the idea that you inject microwaves and you see a resonant enhancement of the energy that increases the escape rate, and doing that experiment to really figure out what's going on with the parameters in the system. And that really set us on the right road. And the other thing that happened very early on is we did the experiment not in a very complicated dilution refrigerator that we had to build, and that takes a long time. We just did it from 1 to 4 Kelvin, where you just take helium, which was available in the lab, liquid helium, and pump on it. And when we first did the experiment, kind of in the way that you would typically do a superconducting experiment in the early 1980s, just with wires connected to it, the data made no sense at all. Okay, it was a complete failure. And what we decided then is, okay, we weren't filtering the noise out. We weren't presenting the junction a well-defined structure that, we could model right. And we just, quickly redesigned the experiment. I don't know, it probably took about a month to do that, to redesign it. And then we took data and it was just right on the predictions. And at that point, we knew we were on the right track, and we had to invent a bunch of stuff. But it was like, okay, let's just solve one problem after the other. And, we understood it was a microwave experiment. We understood, you had to filter really well. And, once you got those concepts right, it was relatively straightforward to do it. And it was just a matter of taking data better and better and do more conclusive experiments, and just really trying to put together a well-crafted experiment that everyone could trust.
Of course, also the technology from 80s and now is completely different, so you can help about that. You can help yourself to reach that project you have predict.
On one of the papers, which is the resonant, the energy level paper, there's a plot with 3 little peaks to it. And it's not a very good figure by today's standard. And that's because the only output we had from our experiment was a dot matrix printer, okay, that made very little dots. So we gave that to the drafts person who, built the title and everything. But yeah, we didn't want to go over 100 or so points with extra dots. So yeah, you could kind of see that it was rudimentary experiment there, but but still sophisticated enough, with the waves and the like, that we could do it right. But yeah, things have progressed so far beyond that. It's really good.
Yeah. Why were superconducting circuits is the right platform for that result? Which design's choice made the difference?
That's really interesting. What happened is there was a proposal on what to measure, and then we invented, with the microwaves, seeing the enhancement through the microwaves. But the kind of the design, the rough concept design was already there, but it was really we learned soon that it was a microwave experiment, it was a low noise experiment, and that was the key thing to think about. And once once we did that, things progressed. And if you look at superconducting qubits right now, everyone intuitively understands it's a microwave experiments, and we do a lot of technology based on that. But it was just not at all clear at that point that that's what you needed to do. And most of the time with these kind of condensed matter experiments, they were like DC-IV curves or very simple data taking. And I think we brought a lot to the field by pointing out that you have to think about this in terms of microwaves.
Does your deep understanding of the law of physics change how you think about big human concept like free will?
So you're going very philosophical. Let me back up for a second.
Yeah.
So we did this experiment, fundamental experiment, quantum mechanics, great. But especially as a student, you've just learned quantum mechanics. We've learned a little bit about this, but I really wanted to understand quantum mechanics very deeply. And one of the nice things about doing, qubit experiments and quantum computing over the years is I've got opportunity to go deeper and deeper and understand it better and better. And although, quantum mechanics in the beginning is very mysterious, at this point, I've done enough experiments and thought about it enough. It just seems like a normal phenomenon for it. It just has different laws than classical physics, but it has, it's all predictable. I kind of understand what's going on. Now, that's not saying that there aren't some other things to understand about quantum mechanics or understanding it more deeply. But at least I feel that's right. So I'm very much in the idea that if I can, predict the result of an experiment, even though all the steps of that prediction philosophically may not be, completely understood, I'm still okay with that. And I'm trying to build a quantum computer. I know what to do. Now, Michel Devereux, on the other hand, still thinks about this a lot, and been thinking about more of the philosophical. And I think this is very French, because the French really like to understand very deeply from, first principles and a philosophical point of view how this works. And what Michel has told me, that quantum mechanics was not really taught in France up until starting around 1962, and then kind of done off to the side, because the French theoreticians didn't like the foundations of this, which is still kind of murky. Whereas I think for Americans, more practical minded, well, as long as you know the machinery and can predict the result of experiment. So that's kind of where I stand philosophically. I still think it's interesting, but I think more thought is useful on this.
Yeah, right. Okay. So, well, about the future. Well, classical computing gave us the internet, artificial intelligence, and smartphones. Looking ahead to 5 to 10 years, what a similar world-changing revolution do you believe quantum computing could unleash, either in our daily lives or in applied science, maybe?
I'm old enough to be around before computers were, around everywhere. And in fact, I built my first computer from a kit in 1978. I built an Apple II. It actually was from a circuit board that had a serial number below 1,000. So it was one of the first 1,000 circuit boards that they built.
Wow.
Okay. So I played around with it, but I knew what it was like to do that. And, it takes a long time for the technology to get out to the ordinary person. But of course, in the beginning, there were a lot of, important things that the computers were doing. So I consider first this to be a supercomputer and to be a tool for solving, various difficult problems. The problem I think that's most likely that we understand the best, it doesn't mean that other people won't come up with other ideas, but the one that I can understand the best and kind of predict the best is, chemical simulation, material simulation. These simulations are very hard because of the quantum mechanics that's involved in simulating how atoms and materials work. And there's some natural mapping between qubits and a quantum computer in doing that. So I kind of like that applications. There's a lot of work going on there, and that seems like something we can do. And in fact, in the consortium, we have some applications we talk about doing that for. So that's what I think about, and I'm excited about. And just an example, right now, people, build with these exotic materials, a lot of important things. There's been the idea of rare earths and the supply chain of rare earths being, really important that we have to worry about in the future. And if we can, let's say, instead of building it out of a rare earth or build it out of a less rare earth, that's cheaper, or let's say more ecologically sound to mine and refine, then that would be a big benefit to humanity. And by having an easier way to make materials and understand their properties and the like, that could make a huge impact. And, with cheaper manufacturing, safer manufacturing, that's a big thing. And it's also quite valuable too, the ability to do that.
Yeah. So, of course, quantum computing will be essential for solving problems that are impossible for today's computers. That's a great point, like simulating new materials or designing life-saving drugs.
Yeah, exactly. And that's what people are talking about. And, but the problem is the quantum computers, we're building quantum computers right now, but they're quite rudimentary. We have to make them better. We have to make more of the qubits and the like. And it's a big problem to fit a complicated real problem to the small quantum computers we have. But people are working at it, and that gap is getting close, is getting close. And, that's what's exciting about the field is so many people are working on it to, close that gap and to make it valuable. And what's nice is once you start solving real problems with it, and frankly, people are making money off of that, then with that funding, you can then reinvest into the field and make better quantum computers. So that's the big moment. It's almost a business case, okay? But that's a big moment. But this is what happened with regular computers, is they got into what's called the virtuous cycle, where they were valuable enough and making enough money from their applications to then, put more effort and time and research into doing it. And that's what we want to think about.
Okay, John. And the last question, and then we are going to finish. What is the one thing you wish every person understood about the beauty and value of science?
Well, I don't know if I can say one thing, but I'll make a good comment. I'm doing science to be very beautiful and artistic. If people are an artist and they're painting or they make a piece of art, that's very satisfying. And in fact, doing science has the same feeling. Only here we're learning something fundamental about nature or the way we put things together, and it's quite the thrill to be able to do that, to discover something new. And then on top of that, it may not be evidence in whatever you did or paper you wrote or whatever, but there's this idea that this could eventually be useful to humanity, and you can use these ideas to do something practical and helpful. So the combination of the beauty of science and also the practicality of it, the value of science, is quite great. Okay, I really like being a scientist because of that.
Thank you very much for your time today and for sharing your insight with us. It was an honor to talk to you. Diego and Flor saying their regards, and this will be very helpful for our students and our astronomy community. We are a few, but we are, so thank you very much.
Yeah, and thank you. You asked a couple questions. Thank you for thinking about that. That was, I enjoy these interviews because I think about science and what we did a lot of times in a new way, and that's really pleasant. So thank you.
Thanks.
Yeah, that'll be a nice that was a nice series of Q&A session. Sometimes better than some of the reporters I have.